All right, so looking at example 3c, it says find the coordinates of all relative extrema for the following function. That means that I want you to find both the y value, which is the actual max or min, and then the x value where it occurs. So if you ever see the word of, that means you're talking about the y value. If you ever see the word at, it's talking about the location. So for this one here, since that's not something I would expect y'all to be able to do without a calculator, you're going to go ahead and graph it. So to graph it, and again, we kind of went over this on Thursday, you go to y equals, I am back in math print. So if you have the classic print, just be careful the way you type it in. So we'll just type it in x square root of, and in math print, it'll keep you under the radical until you click to the right. If you're in classic print, you're going to have to put the parentheses. I think it opens the parentheses for you, and then you close the parentheses when you're done with the radical. So a quick double check, triple check to make sure you're in there correctly. And if you're not sure what the graph looks like, zoom, what? You can do zoom 6, which is your negative 10 to 10. Zoom 5 also works. That's your square window. What that does is it makes the x and y pixels the same length, and so you end up having more width on your graph than you would height because the graph screen is wider. But I like zoom 6. All right, so there's my graph right there, and that's not very helpful, right? It looks pretty small. I can't really discern what's a max or min there. So now we're going to zoom in. And in this case, instead of just zooming in, which always zooms in at the same scale, zoom box is kind of nice. So I'm going to choose zoom box. Now what you do for zoom box is you define one of the four corners of a rectangle. I always like to start in the top left. So I'm going to scroll up here to the top left, maybe click to the left a little bit of the y-axis, and I'm going to hit enter. And what that does is it locks in one of the corners of these rectangles. And almost like a cell phone then where you drag, you're going to click to the right to make the width of your rectangle, and then you're going to click down to make the height of your rectangle. And what that allows you to do is basically zoom in and change the scale of your x and y axis. So once you think you have your graph entirely contained in your little rectangle, hit enter, and now you get this graph right here. Okay? So it looks like the function starts off increasing up to about right here, and then it's decreasing. And notice that it doesn't quite connect with the x-axis right there. It's because your calculator is in function mode, and if you click mode, see it says function, and it knows that functions aren't supposed to be vertical lines. So it doesn't draw a little vertical line piece there. But the graph does actually go down and stop right there on the x-axis. All right, so let's go ahead and figure out what that value of the x and y value up there. So second trace, that's your calculate graphing menu. And we know it was a high point, so we're going to select number 4. Left bound, we're to the left of the high point, so click enter. And then you can scroll until you can visually see that you're coming down, and make sure you are to the right of it. Hit enter, and then you can just hit enter for your guess. And so there you go. We'll say that this is a what? Is it a local max or a local min? It's a local max. So we'll say G has a local max of, and remember the y value is the max, so y equals 3 decimal places 0.324. That's if you truncate, or 325 if you round. And then it happens at x equals 0.749 if you truncate, or 0.750, you would need that 0 if you round. And that looks like it's the only place. This is x equals 1 right here. So here's what I wrote down. Local max of, and then at. Now, is that also the absolute maximum or the global maximum? Yeah, it is. So we could say that as well. Has a local max and a global. I'm just going to add that underneath here. And a global max of y equals that at x equals that. Based upon that, you can get intervals of increasing and decreasing. Watch this. We could say that G is increasing, INC, on the open intervals from 0 to 0.749. That's the x value of the local max. And it is decreasing from 0.749 all the way up until that value on the x-axis, which is at 1. So you can write that. G is increasing from 0 up to the x value of the local max, and it's decreasing from the x value of the local max up to x equals 1. Now, there's one last thing I want to talk about. That is the minimum values. Does this function have a local minimum? Well, that's kind of a trick question. Local minimums can only happen on an open interval. So let me ask you this question, which is a little bit easier. Does this function have an absolute minimum? Is there on this graph a y value that is the absolute lowest y value on the whole graph? I think it does, right? If you look right here, remember I said this one does go to the x-axis. So at x equals 1, we do get 0. And you can verify that by hitting the trace button. If you type in a 1, notice it'll tell you that y is equal to 0. And it'll put you blinking on the x-axis. But if you look right here, it almost looks like it starts off by going below the x-axis, doesn't it? Almost. So let's do this. Let's go zoom in. I'll use the zoom in feature this time. And let's type in zoom in, number 2. And I'll just scroll back over here. And let's see what's going on right in there. Looks like it is not dipping below the x-axis, actually. I'll zoom in again. If I keep zooming in, it looks like it's actually just rising straight out of the origin. So if I hit the trace button and type in a 0, it shows that y is equal to 0. So what looked like it may be going down a little bit and crossing the x-axis and then coming back up, it actually did not. So this is using your calculator in the correct way. You're using it as an exploratory tool, using the zoom feature, using the trace feature to figure out what's happening. So with that in mind, then, do we have an absolute minimum value, a global min? What's the lowest y value on the entire graph? 0. Yeah, we have a global minimum of y equals 0 at x equals 0 and at 1. It occurred at 2 different places. You can only have one global min or one global max, but it can occur at more than one place. Now notice, once we have the global min and the global max, we could figure out what the range of this function is. The domain appears to be the following. The domain of G appears to be all the values between 0 and 1. So that would be the domain in interval notation. And you could verify that by solving the inequality if you want. X minus x squared, remember, has to be greater than or equal to 0. I'm not going to solve that because we have the graph. But the range is something that's relatively hard to get without the graph. And once we have the graph, we can get the range. What was the lowest y value for the range? 0. And what was the maximum value for the range? It was 0.324. So 0.324. And so there you go. Just by finding one point on the graph, we can answer all of those questions. Where is there a local max? Where is there an absolute max? Where is there a global min? There is no local min. What's the domain? And what's the range? And what's the interval of increasing, decreasing? All because of that one ordered pair. Okay, any questions on how to use the calculator to find your maximum slash minimums? Okay, let's look at an application. We're going to look at average rate of change, average rate of change. If you have something that is curved, let's say it looks like this. It starts at 0, and then it goes up at a variable rate from 0 to, let's say, 2. Okay, and if this function is f of x, the average rate of change ends up being the slope of this line right here. If I could find the slope of that line, this is called a secant line. A secant line essentially connects 2 points on a graph. Is what you call the chord in geometry. It turns out that the slope of that line is not only the slope of the line, it is the average rate of change of that function, in this case, from 0 to 2. Bless you. So when you talk about how the graph gets from left to right, it goes up pretty rapidly, and then it flattens out, and then it starts going up rapidly again. So the rate at which it's actually traveling from left to right varies. The y values go up and down at a variable rate. But if you wanted to see how on average it got from here to here. That would be like if you wanted to set the cruise control at one speed and get to the same place in the same amount of time, that would be the slope of this secant line. It's going up and over, up and over, up and over, up and over, up and over at the same rate all the way across. So how do you find the slope of a line from Algebra 1? Rise over run. Yeah. So we're going to call this the change in y over the change in x. And for change in, we use the little Greek symbol delta. Okay, it's a triangle. Well, what that really is, it's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We call that right there the difference quotient. So that's kind of some terminology. The difference quotient is a very appropriate name because we are dividing quotient two things that are being subtracted. All right, so the slope of the line in Algebra 1, hopefully you worked applications. It was the rate of change that was average and instantaneous because the slope of a line is the same. Oh, so for us, it would be specifically f of 2 minus f of 0 all over 2 minus 0. And if I knew what the function equation was, I would be able to compute f of 2 and f of 0. So the change in y over the change in x. That's the slope of the secant line, and it's the average rate of change. Now, when you start looking at the average rate of change of position, you get something that's a little more meaningful. If we were measuring position, let's say, I'll call it x of t. Let's say we're measuring our position in miles against our time value t in hours. If you were to find the slope of a line here, it would be units of y over units of x, right? It's a quotient. So what would the units of y be? Miles divided by units of time in hours. And the way we would read that is miles per hour. So the average rate of change of position is called the average what? What do we measure in miles per hour? Speed, yeah, or more specifically, velocity. Velocity is a vector. It has direction, whereas speed is just the scalar quantity with no direction. So the average rate of change of position is average velocity. And if you ever take a physics class or an introductory to physics, you will learn that it's displacement over time. Displacement over time. Well, the displacement is just the change in the position over the time. The elapsed time is the change in time. All right? So here's the definition. The average rate of change of a function on a closed interval for f of x between two arbitrary values. Call it x equals a and x equals b. The average rate of change then is going to be f of b minus f of a over b minus a. And of course, all right, no, that's kind of like cool music for a timeout. If I'd have known, I could have taken a timeout. Had somebody shoot like a half-court shot to win groceries for a year and then get back to it. All right. So here's the graph, essentially, of what I just showed you in my introductory speech here. You have a curved graph. So the y values are changing at a variable rate. The steeper the graph, the faster the y values are changing. The shallower the graph, the slower the y values are changing. But on average, you can find the rate at which you would get from one point to another by finding the slope of that line connecting the 2 points, which is called the what line again? Secant line. Yeah. It's f of b minus f of a over b minus a. All right, I think you have it. Okay, we've talked about it quite a bit here in the last couple of minutes, including the timeout. Here it says to sketch the function without a calculator, so even though you have it in front of you, and then find the average rate of change on the following closed intervals. All right, so our function is x minus 4 quantity squared. Step 1, what's the parent function? X squared, sweet. So that's the smiling, opening up parabola that bounces at the origin. What does the minus 4 do to this graph, as it would do to any function? Right 4. Yeah, it's on the inside, it's with the x, so it's going to affect the graph horizontally. So it's going to come over here to 4. And I'll just put a little dot there, that's the vertex. It opens up that way, and it opens up that way. All right, here's what I want to do then. For that graph, I want to figure out what is the average rate of change on the x interval, closed interval, from 2 to 4. So I'm going to show that first. we come over here, 2 is going to be somewhere right about here, the halfway point. So there would be the dot at 2, there would be the dot at 4. If you want to draw a line that connects them, something like that, or if you hold it for a while, you can snap it straight. That would be the secant line. And I want to figure out what the average rate of change is on that graph between those two values of x, from 2 to 4. So here's what you're going to write. When you're doing these types of calculations, you're going to write the average rate of change. You could put ROC. I'm okay with that, ROC. The average rate of change is equal to f of 4 minus f of 2 all over 4 minus 2. You are going to show me the difference quotient, and I'm going to abbreviate that DQ. You're going to show me the difference quotient. Once you set it up like that with the difference quotient, now you can plug in the numerator to get the y values. So what would f of 4 be without a calculator? 4 minus 4 is 0. 0 squared is 0. Minus f of 2, when you plug it in, 2 minus 4 is negative 2. Negative 2 squared is positive 4. And of course, now on the bottom, 4 minus 2 is 2. So you end up with negative 4 over negative 2, which is negative 2. Now, there are no units on this one because I didn't give you any units. But again, if you were measuring miles or feet or something like that on the y-axis and time like in hours or seconds, this would be the average velocity on that 2-second interval. Okay, so that's the slope of the secant line, and it's also the average rate of change of that function on that interval. All right, so now from 5 to 8, let's draw it first. It's always nice to kind of have a visual. 5 is going to be right here, and 8 is going to be somewhere right in there. And so this secant line is going to be positive, and it should be a little bit steeper than the one that we just saw that was negative. So I want the slope of that secant line, which is also the average rate of change. So what are we going to show first? We're going to write average, AVG is fine, rate of change, ROC. You want to get in the habit of labeling your quantities. And the first thing I want you to show is this, f of 8 minus f of 5 all over 8 minus 5. Now notice the two different ways I can give you a closed interval. On part A, I said bracket 2 for bracket, and over here I did inequality notation. But because they have equal signs, it's the closed interval. So two different ways to write the same thing. Now we'll figure out what the solution is. F of 8 is what? You plug an 8 back in up here to the function, you get 4 squared, which is 16. And then 5 minus 4 is 1. 1 squared is 1. All over 3. You end up with 15/3, also known as 5. So that graph did not go 5 units up and 1 to the right the whole time from 4 to 8. Okay, it started out slower than that and then got steeper and steeper. But that would be, on average, how it could get from this point to that point. Up 5 over 1, up 5 over 1. All right, go ahead and set up and evaluate the next one on your own. One thing about notation, because I want you to practice it and looking around, I don't see it. Once you say average rate of change equals the difference quotient, if you're going to evaluate the difference quotient, and you're by working straight down, you're going to have to write your equal sign each and every time. All right, go ahead and set that one up. I'll do the same thing. And we'll meet you back here in about a minute. So if you draw what's going on here, we're going from -1 to 9. So here on the parabola is -1, and 9 would be way up there. If you draw the what line connecting the 2 points? Secant line. You're looking for the slope of that line. The slope of that line is the average rate of change. So what you would show me is average rate of change equals f of 9 minus f of -1 over 9 minus -1. Or you could call that 9 plus 1 if you want. That's fine. What do we call this? The, not Dairy Queen, not disqualified, but difference quotient, the other DQ. Yeah, difference quotient. Now, because our function is given and it's pretty easy to plug those in and evaluate it, we did that on part A and B, I want to show you another way to do it. Let's say you had a function that was kind of ugly and you couldn't just plug in the values without the help of a calculator. Here's how you can do this on a calculator and never worry about rounding error. If you go to y1 and type in x minus 4 squared, you can go then to your home screen and you could type in a difference quotient on your calculator. If you have classic print, you're going to have to use parentheses for your numerator divided by parentheses for your denominator. But if you have math print, if you hit alpha y equals, that's F1. Notice number 1 is n divided by d. That's numerator over denominator. If you choose that, you get a horizontal division bar, which is much safer than a slanted one. You could then type in f of 9. Well, where did we type our function f? In y1. So to access the equation you typed into y1, all you have to do now is hit alpha trace. That activates the F4 menu. And there's the shortcut to all of your things. Now, if you don't have the math print, the way that you access that is by doing the following. You go vars, which is right to the left of clear, vars, that stands for variables. Click to the right to y variables, and then we're in function mode, so hit enter, and there they are. So vars, click to the right, y vars, function, and there they are. So I'll access it this way. So there's y1. If you open parentheses, plug in your input and close parentheses, your calculator will acknowledge that as f of 9. It'll plug in a 9 into what you have stored in y1. Then you could just go minus and do the same thing. Alpha trace number 1 of -1, and then divided by 9 minus -1. And there you have it all typed in on your calculator. It looks pretty much exactly like you would do on your paper. If you hit enter, your calculator gives you the answer of 0. Now, notice my slope does not look like a slope of 0 on my graph. Why not? It's a sketch, and I didn't really draw it to scale. It was just there to kind of inform me kind of some general trends that were going on. The math, though, the calculations, they don't lie. So what type of line should it be between -1 and 9? It should be a horizontal line. Yeah, that's the line that has a slope of 0. So one more time, if you don't have math print, I'll show you what that calculation looks like. After you type it in y1, you open parentheses for your numerator, and you go vars, y vars, function, enter, of 9, minus, again, vars, y vars, function, enter, of -1. Close it for the function, close it for the numerator, and then divided by 9 minus -1, you could just divide by 10. But if you didn't want to do that, then you'd have to open another parentheses, 9 minus -1, close it. So with the classic style, you need to make sure you have parentheses around all of your quantities. You'll get the same answer if you do that. Okay? So the average rate of change was 0. Notice that that was not the rate of change the whole time. The graph was decreasing and then increasing, but on average, it's like it didn't go anywhere. It returned to the exact same place where it started vertically. The displacement was 0. All right, so now here's an application that actually has units. Instead of just working with an arbitrary graph with no units, it says when a pre-calculus textbook. Anyone ever seen one of those? Anyone ever been to a math museum and seen the textbook there? Kind of rare these days. When a pre-calculus textbook is dropped off the top of a tall tower, who would do such a thing? Well, people sometimes back in the day, when they got frustrated with Precal, they would take it out on something, and they would take it out on their helpless pre-calculus book. It kind of made them feel better if they hurt their book. Take that, math. You've been causing me pain and anguish all year long. Now it's my turn to return the favor. The distance that it has fallen t seconds after it was released was given by this function d of t equals 16t squared. All right, so what are the units of t? Seconds, right? And what are the units of d for distance? It doesn't really say. Let's say it was we're measuring it in feet. Okay, feet. Find the book's average speed over the following intervals. So this is from t equals 1 second to t equals 5 seconds. So that's a 4-second span. So now we're going to write the average speed instead of just rate of change. Average speed now, our function is d, so it's going to be d of 5 minus d of 1, all over 5 minus 1. So that's its displacement, its final position minus its initial position, all over the change in time. Well, here's one where I'm going to go ahead and use the calculator. So if you have your calculator in front of you, let's go ahead and evaluate it in the calculator. We'll go to y equals, and we'll type in 16, and we'll use x instead of t. Whatever variable you have on your paper, it doesn't matter. Your calculator is always going to call that independent variable x. So now that we have it in y1, I'm going to switch back to math print here. We're going to type in the ratio that we set up, this one right here, the difference quotient. So how do we access the horizontal division bar? Alpha F1, right? Alpha y equals, and it's number 1, numerator over denominator. Because we put our equation in y1, we can hit alpha trace, which is the shortcut. There's y1 of 5, close parentheses, minus, do it again, alpha trace number 1 of 1, and then we divide it by 5 minus 1. Now, you can also just type in 4, but when you type in 5 minus 1, you can see the difference quotient. And by the way, remember I said I want to see the difference quotient? So when you're setting it up, don't call 5 minus 1 4. Just call it 5 minus 1. I have to see that you're subtracting or adding two different things and dividing them out. Now, the advantage of going to the calculator here is, number one, it'll do all the calculations for you, but because you're typing it in one expression, if these numbers are not exact, you don't have to worry about writing down intermediate values with decimals, storing them, and then typing them all together at the end. It'll compute it, store it, and give you one answer at the very end. 96. So it was a terminating number. And what would the units be if we're measuring the height in feet and the time in seconds? Feet per second. Feet per second. So the interpretation of this then would be, on the 4-second interval from t equals 1 to t equals 5 seconds, the book was falling on average at 96 feet per second. Does that mean it was going 96 feet per second the whole time? No, because we know how gravity works, right? When things fall, what happens to their speed? It increases, yeah. So that was the average speed. It probably started slower than that and probably ended faster than that. Here's what we want to do now. We want to do the exact same calculation. We want to do it for arbitrary values. We want to go from a to a plus h. So we're looking at the interval from a to a plus h, where h is going to be the time difference, or the change in time. So let's go ahead and set it up. The average speed, it's going to be d of a plus h minus d of a all over a plus h minus a. So I'm doing this for arbitrary values. In the previous example, our a was equal to 1, and since 5 was 4 seconds away, the h was equal to 4. Now let's simplify this before we set it up. It's d of a plus h minus d of a, and what does the denominator simplify to? H. Take a good look at this before we set it up and evaluate it. Do you recognize that from anywhere? You should. This is my favorite problem. Exactly. It's shown up on the previous two exams. So this is why it's my favorite problem. You didn't know it at the time, but you were computing a formula that gave you the average rate of change from A to a time that's h units away from that. So if we set it up for hours, it's going to look like this. D of A plus h, well, we're going to plug in for t in our function right here, and A plus h. So this comes out to be 16A plus h squared minus D of A is just 16A squared all over h. Plugging in an A plus h for t, and then plugging in an A for t. There's the setup. Now all we have to do is expand it. So we'll square multiply double square, A squared plus 2AH plus h squared minus 16A squared all over h. Hopefully, once you set it up, the calculation should be routine. We've practiced this enough. Now I'll distribute the 16. You get 16A squared plus 32AH plus 16h squared minus 16a squared all over h. And just like before, if you set it up and expand correctly, good things should happen at this point. Namely, everything without an h should cancel, and it does. And so in the numerator, the only two terms that are left have an h in them. So we'll factor that h out, and we're left with 32a plus 16h, all divided by h, and then the h's divide out, and we're left with 32a plus 16h, which if you want, you could factor out as 16 and call that 16 times the quantity 2a plus h. And what that does is it gives you a formula for the average speed. This is how your formulas in physics come into existence. You do a certain calculation using letters to represent numbers, and if you treat them as constants all the way through, then at the end you can get this distilled-looking expression or formula, and now you can let the letters become variables again. So this gives you then, for that problem, the average speed between any two times during its fall, where A is the starting time and h is the distance between the starting and the ending time. Let's verify this. On example A, we went from t equals 1 to 5. So the A value was 1, and the h was what? If we started at 1, h is the distance between your starting and ending time. How many seconds did we let elapse between 1 and 5? 4, right? 5 is 4 units away from 1. So if I use those variables, or those values for the variables right here, I should get the same number. Now the average speed, if I plug them in, is 16 times 2 times 1 plus 4, which gives us 16 times 6, which does come out to be 96 feet per second. But now if you wanted the average speed between like t equals 1 and t equals 2, you wouldn't have to set your difference quotient up all over again and compute it. You could just plug it into this little formula right here. So this is the step beyond the concrete. The actual example, this is looking at it in a more abstract way, creating a formula. Now when you get to calculus, calculus is all about the study of how fast something is traveling at a single instant in time, not between 2 points in time. This becomes increasingly important when we establish what's known as the derivative, which will eventually be the formula that tells us how fast it's traveling at any given moment. All right, any questions on average rate of change? Average rate of change. When you set it up, you're always going to show me the difference quotient. And it turns out that it's the slope of the what line? Secant line, right, connecting the 2 points on the graph. All right, we got 8 minutes left. Let's go ahead and look at another property of functions that's very important. We're going to be looking at symmetry. Symmetry of a graph is going to be helpful when you're trying to sketch a function or just describe the function. There are two types of symmetries that we're talking about. We're talking about y-axis symmetry and origin symmetry. All right, so here's the graph right here. It's in red or pink, and we say that this function has y-axis symmetry. And what that means is, if you were to take this graph and fold it on the y-axis, the graph would lay on top of itself. It would perfectly coincide if you folded it along the y-axis. If a function has y-axis symmetry, then we call it an even function. Okay, so this is another definition. And because it's a definition, it's an if and only if. So if I tell you that we have an even function, you know it has y-axis symmetry. If a function has y-axis symmetry, then you know it's an even function. And it's pretty easy to spot graphically. If you have the graph in front of you, you just imagine folding it on the y-axis, and if the graph lines up with itself, it's going to have y-axis symmetry. Well, we want to develop an algebraic way to determine if it's an even function, because graphs are not always easy to produce without a calculator. So here's the algebraic consequence of an even function. If you were to pick a random x value and pick the opposite x value and evaluated the function at both of them, because of the y-axis symmetry, as long as you're computing the y value at the same distance on the other side of the y-axis, you're going to end up with what? You're going to end up with the same y value, right? So whether you plug in a positive x or a negative x, like a positive 5 versus a negative 5, or a positive 10 versus a negative 10, because of the y-axis symmetry, you're going to get the same y value on either side. So if this function is called f of x, here's the way to write that algebraically. F of negative x is equal to f of positive x. This is the algebraic consequence, and this then becomes the algebraic test for an even function. If you replace x with negative x and you end up with the exact same answer that you started with, you're going to have an even function. It has y-axis symmetry. The other symmetry that we're going to be looking at is not x-axis symmetry, because if a function has x-axis symmetry, more than likely it's not going to be a function. If you folded this on the x-axis, this might line up with that, but it would fail the vertical line test. So we don't look at x-axis symmetry. We call it origin symmetry. Origin symmetry. And you can think of origin symmetry as being a rotational symmetry, not a folding symmetry. If you were to put your finger down at the origin and spin the graph 180 degrees, that would be equivalent to you taking your graph on your iPad and just turning your iPad upside down. If the graph looks the same after you spin it 180 degrees around the origin, then it has origin symmetry. Any function that has origin symmetry, then we call an odd function. And that's pretty easy to remember because both origin and odd, neither one of them have a z in it, right? So it helps you remember. They also both start with O. That's actually a little bit more helpful. Odd functions have origin symmetry. A function with origin symmetry is an odd function. Now we want a graphical consequence that helps us develop an algebraic consequence. So here's what we're going to look at. If you plugged in a positive x, and then you went the same distance on the other side and plugged in the negative version, for an even function, you're going to get the exact same y value. But for this one, you don't get the exact same y value, you get the what? Because if you rotate it around, this y value here that's positive is going to end up being negative. So you don't end up with the same y value, you end up with the opposite y value. Okay? So opposite x values give not the same y value, but gives opposite y values. Opposite x values give opposite y values. So the way that you write that in function notation is the following. F of negative x is equal to the opposite of f of positive x. This becomes the algebraic test for an odd function. You are going to replace x with negative x, and if you get the opposite of what you get when you plug in a positive x, the function is going to have origin symmetry and therefore will be an odd function. Okay? So real quickly, a recap. If a function has y-axis symmetry, it's a what function? An even function, right? And opposite x's yield same y value. An odd function has what type of symmetry? What's that? Rotational, which is formally called origin symmetry. But yeah, it is the rotational symmetry. and opposite x's there give you opposite y values. Okay, so we'll stop right there. You got 2 minutes left to turn in your calculator. Tomorrow we'll do PSAT stuff. Make sure that you type in your answer choices to that Google document, and we'll spend all 50 minutes tomorrow going through as many PSAT math questions as possible so that y'all are ready to go on Wednesday.